about. Okay, so let's move to the basics. So when I say, at the beginning, I said today's session is all about low pass filters because, I just wanted to focus on this, section about low pass filters. So typically speaking, when you make a low pass filter, you have a few options, okay? You can choose the very simple component. So here, as I show you, right, you can either use a inductor, which is a high impedance component when it comes to high frequency, because the impedance really of a inductor is 2 pi FL. Everybody knows this equation, right? So as your frequency increase, given the same inductance value, then this impedance basically starts increasing. And if you look at the capacitors, the impedance is 1 over 2 pi FC. So that means given the same capacitance value as your frequency increase, your impedance starts to drop. So that's really the most fundamental parts of filter, right? Everybody understands this, L and C, okay. But most of the time, people make low-pass filter for EMC applications. So here, again, you have two options. So you can either choose a LC filter or a CI filter, but depends on your application, as you can see here, right? So in this diagram, what we're talking about is purely differential. So when we say differential mode, let's say this could be your live or neutral, or this is your power, let's say 12 volts and 0 volts, or this could be a CAN bus plus, CAN bus negative. So this is really the differential mode we're talking about. But it's the principle is the same for common mode as well, as we will discuss later. But really, you can see the performance of a filter depends actually on two things. One is on the source impedance, okay? And the other one is the load impedance. So yeah, depends on whether it is low high or high low or low low, you could have very different performance, okay? So that's why most of the time people would opt for a more sophisticated filter configuration, such as a pi filter. So in this case, you can see a pi filter consists of CLC, basically forming like a Greek letter pi. And we also can make a T filter. That means you use two inductors and one capacitors, right? One capacitors, and then that's a T filter. Now, you will find most of the time people use pi filter. There are a few occasions people use T filter. And you may wonder why people prefer a pi to a T filter. Okay, so we'll answer that question in this slides. So again, this just quickly show you a simulation results of a pi filter against T filter. Now, there are a few things I need to highlight on this slide. First, let's have a look at the simulation model I built. In this case, I have a source. This represents a noise source, okay? And I have a small resistor. This resistor really just represents the impedance of my source. So in this case, you can say it's 5 ohms, okay? And then I have a load, which in this case is 100 ohm. That means, relatively speaking, is a high impedance load. So in this case, we have a low-high configuration between the source and load. And we are doing a simulation looking at sort of the dB reduction, if you treat it, of a pi filter and of a T filter. But interesting is, right, some of you, especially the sort of senior level engineers, will say, well, man, this is ridiculous. You just built a CLC. You don't even take parasitics into your simulation. Yes, but what I wanted to demonstrate in this simulation is just to really show you the difference when using pi and T. So ignoring the parasitics for now, okay? We're going to discuss that later. But as you can see in this case, when you have a low-high configuration, that pi filter actually performs better than T filter. But when you have a sort of a high-low, relatively speaking, configuration, then pi and T perform very similar, okay? And some of you may also spot right here, if you look at this region here, you can see that sometimes, I mean, in this case, it's not bad because even in the worst case, let's say at 21 kilohertz or 22 kilohertz, you have almost like no effects of this filter. But sometimes you can see in the manufacturer data sheets, when they show you the insertion loss, sometimes they even have something like this. So that means this actually is not even filtering the noise, it's amplified noise, okay? So that's another thing you need to know. But yeah, as you can see, because of the performance, based on these two simulations, I would say, yeah, I would prefer a pi filter in general, okay? There are many other reasons that I would prefer to choose a pi filter over a T filter. So for example, cost-wise, so if I make a pi filter on a PCB, all I need is an inductor and two capacitors. These two capacitors might just be surface-mounted multi-layer ceramic capacitors, right? So if you look at the cost and the size, I mean, this is really good. Whereas if I use a T filter, then we're talking about two inductors. Inductors, generally speaking, are more expensive than capacitors. And you also have to taking into the account of the current rating, the magnetic, saturation of the magnetics and things like that. So yeah, another reason of choosing pi filter over T filter. And sometimes when you have two inductors next to each other, right, next to each other, especially if you work for a volume manufacturers, you're making a filter. And often you don't really select the shielded inductor, right? Shielded inductor is pretty good. I mean, they are widely used for switch mode power supply design, okay? And if you don't use them, then you are inviting a big problem, right? So, but for filter inductor, sometimes you don't really need a shielded inductor. I mean, of course, you can use a shielded inductor, but that just adds some costs. But think about it. If you have two inductors next to each other, you're going to have magnetic flux between the two sort of intertwining to each other, right? And that's what we call a coupling effect, okay? And that means the performance of each inductor will drop, right? Because of this effect. So that's another reason I would prefer pi on a PCB level, definitely, to T. Okay, so let's move to the next. So these are pretty basics. Now we're moving to a slightly advanced subject, which is common modes against differential mode filters. Now, we are not going to spend time today to really explain what is a common mode and what is a differential mode. And I know lots of people understand this and lots of people think they understand it. But really, if you really want to understand what is a common mode and what is a differential mode, you have to see things using field theory rather than using a circuit theory. Because from the circuit point of view, having two currents, like common mode, right? Two currents go in the same direction, it just doesn't make any sense, isn't it? Whereas if you look from the field perspective, when you have a field propagates from the source to the load at, let's say, approximately close to the speed of light. And then that current is just a byproduct. It's a tailing current behind the wavefront. Then you will understand, right? You can cause common mode current flow on the surface, most of the time on the surface of the conductors. And then the return path would be either a chassis or earth or some cable nearby, right? So that's basically what we mean by common mode against differential mode. But as you can see from this diagram, that to make a filter to work for differential mode is actually pretty easy, right? So here you can see it's a pi filter as we explained, and you can see on a evaluation board, this is a MPS evaluation board for a power supply product. And you can see here they have two capacitor and one inductor. So that is the differential mode filter for the noise. And for the common mode, you just make very similar topology, but rather than using an inductor, you use a common mode choke. And rather than using a capacitor between the lines, you use capacitor to chassis or capacitors to earth, right? Depends on how you call it. Yeah, so you can see here is a common mode choke. This is another one. And these two caps here are the common mode capacitors. So they sort of diverts the RF currents go to the earth, and then sometimes they collect the currents so they don't propagate to the wires, which could lead to conducting emission or radiating emission. So that's their jobs, really. Okay. Right. So speaking of common modes and common mode filters, now this is something really interesting, and I like to spend some time talking about it. Is remember on the first slides, I said the performance, the performance of your filter depends really on the source impedance and load impedance. Now, this is actually quite easy if you have a differential circuit, right? So for example, I just draw a very simple buck converter here, let's say. So if I have a buck converter, I have a input capacitor, I have a switch, I have another switch, and I have a LC filter here, and this is my load. Okay, so if I want to design a differential mode filter, right, then I will look at the differential impedance, source impedance. Actually, in this case, the source impedance is here because that's where it's generating the noise, and the load impedance is here.